Hi, welcome back to my class in Advanced Statistics. For today, we will take up the variance or variance and standard deviation of a discrete random variable. And we will also take up the Tchebysheff'S theorem as well as the empirical rule that applies for a distribution of data whose shape is bell-shaped. Now, the mathematical expectation or expected value of a discrete random variable is not a complete or does not provide a complete description of the probability distribution for a discrete random variable. And the concept of expected value is said to be intuitive, which means that if an experiment is repeated many times, the mathematical expectation or expected value for a discrete variable tells us that if an experiment is repeated many times, you can expect to get a value for the discrete random variable that is near or close the expected value or the population mean of a discrete random variable. And that is the reason why it is called intuitive. And the mathematical expectation or expected value or population mean for a discrete random variable is a measure of central tendency for the probability distribution of a discrete random variable. Just as we take the mean, sample mean as a measure of central tendency for the set of observations or values of x. Now, to have a better measure, to have a measure of the spread of the probability distribution p of x for a discrete random variable, we take up variance and standard deviation. First, we define the variance of a discrete random variable. we read the definition of variance or variance of a discrete random variable x. Let x be a discrete random variable with probability distribution p of x and expected value denoted by mu. Then the variance of x denoted by sigma square is defined by this formula. The variance of the discrete random variable x, sigma squared, is equal to the expected value of the square of the difference between the values of the discrete random variable x and the expected value of the discrete random variable x. And by definition of expected value, the expected value of the square of quantity x minus mu is equal to the summation of the product of the square of quantity x minus mu and the probability of x, and we get the summation of this product over all values of the discrete random variable x. The variance sigma square of a discrete random variable x may be computed using this alternative formula. Sigma square is equal to summation of x squared times p of x, and we get the summation of the products x squared and p of x over all values of the discrete random variable x minus the square of mu, the expected value of the discrete random variable x. Based from this definition, for you to be able to obtain the variance of a discrete random variable x, you should know the possible values of x, the possible values of the discrete random variable x, and the corresponding probability for each value of the discrete random variable x. The expected value denoted by the Greek letter mu may also be given, but if you are given the values of the discrete random variable x and their corresponding probabilities, then you can easily compute for the expected value of the discrete random variable x using this formula. From our past lesson, the expected value of the discrete random variable x, denoted by mu, also known as population mean, is defined as the summation of the products of the x, the value of x, and the corresponding probability for that value of x. And we get the summation of this product over all possible values of the discrete random variable x. Now, from this equation, we can say that the variance of a discrete random variable x is the average. Expected value indicates averaging, and this expected value of the square of this quantity x minus mu is the variance of the discrete random variable x. And from this expression, we can say that the variance of a discrete random variable x is actually the average of the square of the deviations of the values of x, the values of the discrete random variable x from the expected value of the discrete random variable x, or from the population mean mu. Now, we will take an example for using this formula and this alternative formula to calculate the variance of a discrete random variable. For our first example, consider the following problem. 3 balanced coins are tossed simultaneously, which means that you will toss these 3 coins at the same time. Let x be the number of tails. That means x is a discrete random variable, and the value of x is the number of tails in each of the possible outcomes when we toss three balanced coins simultaneously. Find the variance or variance and standard deviation of the random variable x. The first step is to list down all the possible outcomes when you toss a balanced coin, three balanced coins simultaneously. And I will use a tree diagram to list down all the possible outcomes when we toss three balanced coins at the same time. In a toss of the three balanced coins, the outcomes for the first coin are heads or tail. That is, either we get a head or tail for the first coin. If we get a head in the first coin, for the second coin, there are again two possible outcomes that we can get. Either we get heads or tail. If we get head in the first coin, in the second coin, either we get heads or tail. If we get heads in the first coin and heads in the second coin, in the third coin, it's either we get heads or tail. If we have heads in the first coin and tail in the second coin, in the third coin, either we get heads or tail. If we get tail in the first coin, in the second coin, there are again two possible outcomes. Either we get heads or tail. If we get tail in the first coin and heads in the second coin, in the third coin, either we get heads or tail. If we have tails in the first and second coins, in the third coin, either we get heads or tail. Our sample space, denoted by capital S, is the set of all possible outcomes when we toss three balanced coins at the same time. And one possible outcome is getting three heads we get heads in all the three coins. Head in the first coin, heads in the second coin, and heads in the third coin. Another possible outcome, heads in the first coin, tail in the second coin, and heads in the first, another second possible outcome, heads in the first coin, heads in the second coin, and tail in the third coin. The third possible outcome is getting heads in the first coin, tail in the second coin, and heads in the third coin. Another possible outcome, heads in the first coin, tail in the second coin, and tail in the third coin. Another possible outcome is getting tail in the first coin and heads in the second and third coins. Another possible outcome, we get tails in the first and third coin and heads in the second coin. Another possible outcome is the event of getting tails in the first and second coins and heads in the third coin. And the last possible outcome is the event of getting tails in all the three coins. And our sample size is n. That means there are 8 possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8. When you toss 3 balanced coins simultaneously. And the probability that each one of these events will happen is 1 over 8. 1 out of 8 possible outcomes. That means each of these events is all the events are equally likely to happen or to occur. Now, our discrete random variable represents the number of tails in tossing 3 balanced coins at the same time. For this event, the number of tails is 0. For this event, the number of tails is 1. For this event, the number of tails is 1. And for this event, the number of tails is 2. Hence, for this event, x is 1. For this event, x is also 1. And for this event, x is equal to 2. And for the last 4 events, the number of tails are 1, 2, 2, 3. Or the values of x are 1, 2, 2, 3. And the probability of each of this event, as I said, is 1 over 8. And we will now construct a compact table for the probability distribution of the discrete random variable x representing the number of tails. And in that probability distribution, we summarize the possible values of x, which are 1, 2, and 3, 0. Which the possible values of x are 0, 1, 2, and 3. And for each possible value of x, we calculate the probability of that value of x using these probabilities of these events with these corresponding values of x. We now construct the probability distribution for the discrete random variable x representing the number of tails when 3 balanced coins are tossed simultaneously. The possible values of x are 0, 1, 2, and 3, which we obtained from the tree diagram we constructed earlier. You can see the possible values of x are 0, 1, 2, and 3. Now we find the probability of each value of x. Probability that x equals 0 is equal to the probability of this event, which is equal to 1 over 8. The probability that the value of the discrete random variable x is 1 is equal to the probability of this event plus the probability of this event. There are 2 ways by which one tail can occur. That is, in this event, where tail occurs in the third coin, or in this event, where tail occurs in the second coin. or in this event where tail occurs in the first coin. Hence, the probability that x is equal to 1 by addition principle for probability is equal to the probability of this event 1 over 8 plus probability of this event 1 over 8 plus the probability of this event 1 over 8, and that's equal to 3 over 8. Now we find the probability that the value of the discrete random variable x is equal to 2, and the number of tails is 2, occurs when we have this event h heads and 2 tails in the second and third coins, or in this event where we have tails in the first and third coins, or in this event where we have tails in the first 2 coins, the first and the second coins. Now the probability that x is equal to 2 is equal to the probability, the sum of the probability of this event plus the probability of this event plus the probability of this event, and that's by addition principle of for probability. The probability of that this event will occur, or this event will occur, or this event will occur is equal to the probability of this event 1 over 8 plus the probability of this event 1 over 8 plus the probability of this event 1 over 8, or that's 3 over 8. And the probability that the value of the discrete random variable x is 3 is the probability of this event. The event that we get 3 tails can happen in only one way. That is, we get tails in the first, second, and third coins. And this event can happen in only one way. So the probability of getting 3 tails or getting this event of 3 tails in the 3 coins is 1 out of 8, or 1 over 8. Now we check if the condition for the probability distribution is satisfied, and the condition says that the sum of the probabilities of the values of the discrete random variable x should be equal to 1. The condition that must be satisfied by probability distribution for a discrete random variable x is that the summation of the probabilities of x, we add the probabilities over all the possible values of x, should be 1. So we add 1 over 8 plus 3 over 8 is 4 over 8, plus 3 over 8 is 7 over 8, plus 1 over 8 is 8 over 8, or 1. Now, to calculate the variance and standard deviation for the discrete random variable x, we need the expected value, or the population mean, for the discrete random variable x. And it is denoted by mu, and it is given by the following formula. The expected value for the random variable, for the discrete random variable x, denoted by mu, which denotes the population mean, is obtained by getting the summation of the product of x and the corresponding probability of x. So we multiply x by its corresponding probability, we have 0 multiplied by 1 over 8. Zero multiplied by 1 over 8 is 0. Next, we have 1 multiplied by 3 over 8. 1 multiplied by 3 over 8 is 3 over 8. Next, we have 2 multiplied by 3 over 8. And we have 2 multiplied by 3 is 6 over 8. And lastly, we have 3 multiplied by 1 over 8. Three multiplied by 1 over 8 is 3 over 8. And we get the summation of these products for the expected value of x. We have 0 plus 3 over 8 is 3 over 8, plus 6 over 8 is 9 over 8, plus 3 over 8 is 12 over 8. And 12 over 8 to the lowest terms is 3 over 2. And 3 over 2 is 1.5. Hence, the expected value of the discrete random variable x is 1.5, denoted by mu for population mean. This mean is intuitive, which means that if we repeat this experiment over and over again, we expect to get the value of x that is very close to 1.5 or near 1.5. It may not be exactly equal to 1.5, because it's not actually possible to get a tail of 1.5, but the number of tails that you will get, or the value of x that you will get if this experiment is repeated again and again, is very close to 1.5 or near 1.5, or if you round this off, near 2 or close to 2. Now we can calculate the variance or variance for the discrete random variable x, denoted by sigma squared. And as we said, the variance for a discrete random variable x is the average of the square of the deviations of x from the expected value of x, or the mean mu. That is sigma squared, the variance of the discrete random variable x, is equal to the expected value of the square of the difference x minus mu. X minus mu represents the deviation of x from the expected value, or from the mean mu. And this is equal to the variance for a discrete random variable x is equal to the summation of the products, the square of the difference x minus mu multiplied by the corresponding probability of x, and we get the summation of these products over all possible values of x. And so we add columns for computing x minus mu, and then x minus mu squared, and the product x minus mu squared times p of x. We start with x minus mu. Our mu is 1.5. We have 0 minus 1.5. 0 minus 1.5 is negative 1.5. Next, we have 1 minus 1.5. The next is 1 minus 1.5. 1 minus 1.5 is negative 0.5 or negative 0.5. Next, we have 2 minus 1.5. 2 minus 1.5 is 0.5. And lastly, we have 3 minus 1.5. The last is 3 minus 1.5 is equal to 1.5. Next, after we get the difference x minus mu, we take the square of each difference. We have 1.5 square The first is 1.5 square, and we have to use our calculator. The next one is the square of negative 0.5. The square of negative is positive. Next is the square of 0.5 is square of 0.5. Next is the square of 1.5. And after we get this column, we multiply the square of the difference x minus mu by the corresponding probability of x. And we get the summation of the last column for square of x minus mu the variance then is the sum of the last column. And we will use calculator to calculate this summation and these products. We calculate the square of the difference between x and the expected value of x or mu. The square of 1.5 using calculator is 2.25. The square of negative 0.5, the square of negative is positive. The square of 0.5 is 0.25. The square of 0.5 using calculator is also 0.25, and the square of 1.5 is 2.25. Next, we multiply the square of the difference between x and mu by the corresponding probability of x. 2.25 is multiplied by the probability x is 0, 1 over 8. We have 2.25 multiplied by 1 over 8. Next, 0.25 is multiplied by the probability x is 1, 3 over 8. We have 0.25 multiplied by 3 over 8 is 0.25 multiplied by 3 is 0.75 over 8. 2.25 multiplied by 1 is 2.25 divided by 8. Next, 0.25 is multiplied by The probability x is 2, which is 3 over 8. We have 0.25 multiplied by 3 over 8. 0.25 multiplied by 3 is 0.75 divided by 8. Lastly, we have 2.25 multiplied by the probability x is 3 or 1 over 8. 2.25 multiplied by 1 over 8. 2.25 multiplied by 1 is 2.25 over 8. And we add the last column. The common denominator is 8. And we have 2.25 plus 0.75 plus 0.75 plus 2.25. Using calculator, you should get 6 over 8. 6 over 8 in lowest terms is 3/4. You divide 6 by 2, you divide 8 by 2. And 3 over 4 in decimal number is 0.75. And this is the variance or variance for the discrete random variable x. And we check this value using the alternative formula to calculate for the variance of discrete random variable x. This is the alternative formula to calculate the variance sigma square for the discrete random variable x. It's equal to the summation of the square of x times the corresponding probability of x minus the square of the expected value of x, or the square of mu, the population mean. And we need the square of the value of x. I will write 2 more columns. In here, I will write the next 2 columns. We need the square of each x value. The square of 0 is 0. The next value of x is 1. The square of 1 is 1. The next value of x is 2, and the square of 2 is 4. And the last value of x is 3, and the square of 3 is 9. Now we multiply the square of x by the corresponding probability of x. We have 0 multiplied by the probability x is 0 is 1 over 8. And 0 multiplied by 1 over 8 is 0. Next, we have 1 multiplied by the probability of x is 1. 3 over 8. 1 multiplied by 3 over 8. And 1 multiplied by 3 over 8 is 3 over 8. Next, the square of 2 is 4, multiplied by the probability x is 2, 3 over 8. We have 4 multiplied by 3 over 8. And 4 multiplied by 3 over 8 is 4 multiplied by 3 is 12 over 8. And 9 is multiplied by the square of the 9 is multiplied by the probability x is 3, 1 over 8. 9 multiplied by 1 over 8. And 9 multiplied by 1 over 8 is 9 over 8. 9 multiplied by 1 is 9 over 8. And we add this column for summation of x squared times probability of x. Common denominator is 8. We have 3 plus 12 is 15. And 15 plus 9 is 24. So here summation of x squared times p of x is 24 over 8. Minus the square of mu. I will use the fractional value of, mu is equal to 1.5. I will use the fractional value of mu of 3 over 2. And we square it. We simplify, we have sigma squared is equal to 24 divided by 8 is 3. And the square of 3 halves is 9 over 4. And we multiply 3 by 4 over 4 so that common denominator is 4. Multiply 3 by 4 over 4, common denominator is 4. For the numerator, we have 3 multiplied by 4 is 12, minus 9. And 12 minus 9 is 3. Over 4. And that is the value of sigma squared 3/4 or 0.75. Hence the value of the variance sigma squared for the discrete random variable x representing the number of tails when 3 balanced coins are tossed simultaneously is correct, which is equal to 0.75. Now, the standard deviation of the variance sigma squared is equal to the principal root of 0.75, or the standard deviation denoted by sigma is the principal root of sigma squared. And the principal root of a real number refers to the positive root of the real number. Find the standard deviation for a discrete random variable. Standard deviation of discrete random variable is defined as the principal root of the variance or variance of the discrete random variable x, denoted by sigma. The Greek letter sigma is the standard deviation of the random variable, discrete random variable, and it is equal to the principal root of the variance. Principal root refers to the positive root of a real number. In our example, we have calculated the expected value of the discrete random variable x, denoted by Greek letter mu for population mean. It's equal to 3 over 2 or 1.5. We have calculated the variance or variance for the discrete random variable x, and we have checked that this is correct, 3 over 4 or 0.75. And our probability distribution for the discrete random variable x is given by this table. For the given variance of 3/4 or 0.75, the standard deviation is the positive root or the principal root of 0.75 or the principal root of 3/4. 3/4 is equal to the square root of 3 over the square root of 4 is 2. And the square root of 3 divided by 2 is 0.87 to 2 decimal places. Or the square root of 0.75 is 0.87 to 2 decimal places. And this is the standard deviation for the discrete random variable x. Now, the expected value or mean and the standard deviation of discrete random variable are used in finding the intervals for which a certain percentage of observations lies in that interval, and the percentage or the number of values that lie within a given interval is stated in a theorem known as Tchebysheff'S theorem. Tchebysheff'S theorem. But before that, we construct the probability histogram for this example. In the horizontal axis, we write the possible values of the discrete random variable x, which is in our example the number of tails when three balanced coins are tossed simultaneously. The values of x are 0, 1, 2, and 3. In the vertical axis, we write the probabilities. And I use a 2-unit intervals in the vertical axis with denominator of 8. So these 2 over 8, 4 over 8, 6 over 8, and 1. And for x equals 0, the probability that x equals 0 is 1 over 8. From 0, we construct a vertical bar with height of 1 over 8. And 0 is at the center of the lower base of the vertical rectangle or vertical bar. This is 2 over 8, so this must be 1 over 8. When x equals 1, the probability that x equals 1 is 3 over 8. From 1, we construct a vertical bar whose height is 3 over 8. This is 4 over 8. So this must be 3 over 8. And for x equals 2, the probability that x equals 2 is also 3 over 8. You notice that we find 1 in the center or the middle of the lower base of this vertical bar or rectangle. For x equals 2, the height of the rectangle is also 3 over 8. And for x equals 3, the probability that x equals 3 is also 1. 1 over 8. And this is the probability histogram for the discrete random variable x. Now we state the Tchebysheff'S theorem, named after the Russian mathematician Tchebysheff. Now we state the Tchebysheff'S theorem, named after the Russian mathematician Tchebysheff. For a given number k greater than or equal to 1, and a set of observations denoted by x1, x2, x3 up to xn, at least 1 minus 1 over k squared lie within k standard deviations from the mean. In this theorem, the given is a set of observations or values denoted by x1, x2, x3 up to xn. In this set of observations, there are n observations or n values. And according to Tchebysheff'S theorem, at least 1 minus 1 over k squared of these distributions of these values or these observations lie within k standard deviations from the mean, where k is a number that is greater than or equal to 1. So the smallest possible value of k is 1. If k is 1, then this expression becomes 1 minus 1 over 1 squared or 0. and that would be when k is equal to 1, then this expression 1 minus 1 over k squared becomes 1 minus 1 over 1 squared, which is equal to 0. And according to Tchebysheff'S theorem, at least 1 minus 1 over k squared of the observations or of these values and values lie within k standard deviations from the mean. This expression within k standard deviations from the mean is equivalent to this open interval from mu minus k sigma and mu plus k sigma. If k is equal to 1, then this open interval becomes mu minus sigma and mu plus sigma. Graphically, this is what Tchebysheff'S theorem says. Suppose this is the graph of the distribution of n observations, and suppose this is the mean of the n observations denoted by mu. From the mean we measure k sigma distance to the right and to the left. From mu we add k sigma, and we get this point. So this point, the distance of this point from the mean is k times sigma, where sigma is the variance and k is a number greater than or equal to 1. We also measure the same distance k sigma to the left of the mean. That is, from the mean we subtract a distance of k sigma and we obtain this point. Thus, this point is equal to mu plus k, this distance of k sigma, and this point is mu plus k sigma. And this point is equal to mu minus this distance k sigma. Thus, this point is equal to mu minus k sigma. And this point and this point is k. This point and this point are said to be k, standard deviations from the mean, because the standard deviation sigma is multiplied by k. So this point is k, standard deviation from the mean, and also this point is k, standard deviation from the mean. And Tchebysheff'S theorem said that within this interval, within k standard deviations from the mean, 1 and 1 minus 1 over k squared of these observations lie in this open interval from mu minus k sigma to mu plus k sigma. That is 1 minus 1 over k squared lie within k standard deviations from the mean. And if k is equal to 0, it means that none of the observations lie in the interval from mu minus sigma to mu plus sigma, which is not very useful and meaningful. If k is equal to 2, then this expression would become 1 minus 1 over 2 squared. And 1 over 2 squared is 1/4. Subtract 1/4 from 1, you get 3/4. And the interval would become mu minus k is 2. For k is 2, this open interval would become mu minus 2 sigma and mu plus 2 sigma. Thus, if k is equal to 2, 3/4 or that's 75% of these n observations lie in this open interval mu minus 2 sigma and mu plus 2 sigma, where 2 is the value of k. That is 3/4 or 75% of the n observations lie within two standard deviations from the mean. If k is equal to 3, then this expression would become 1 minus 1 over 3 squared. And 1 over 3 squared is 1 over 9. And subtract 1 over 9 from 1, you get 8 over 9. And this open interval for k equals 3 would become mu minus 3 sigma. For k is equal to 3, this open interval becomes mu minus 3 sigma and mu plus 3 sigma. When k is equal to 3, 8 over 9, or that's approximately 88% of the n observations will lie in the open interval mu minus 3 sigma and mu plus 3 sigma, or 8 over 9 or 88% approximately of the n observations are within 3. K is 3. 3 is standard deviations from the mean. This mu minus 3 sigma will be the left endpoint of the open interval, and mu plus 3 sigma would be the right endpoint of the open interval. And this point would be 3 standard deviations from the mean. And also this point would be 3 standard deviations from the mean, for k is equal to 3. And the percentage or the fraction of the n observations that lie within 3 standard deviations from the mean is 8 over 9, or approximately 88%. We take an example for applying the Tchebysheff'S theorem. For our example, for the application of Tchebysheff'S theorem, we consider again the problem of tossing 3 balanced coins simultaneously. And we have shown earlier that this is the probability histogram that represents the probability distribution of the discrete random variable x, representing the number of tails when 3 balanced coins are tossed simultaneously. Excuse me. The possible values of the discrete random variable x are 0, 1, 2, and 3. And the probability that the value of the discrete random variable x is 0 is 1 over 8. The probability that the value of the discrete random variable x is 1 is 3 over 8, which means that the number of tails 1 occurs 3 times out of 8 possible outcomes when you toss 3 balanced coins simultaneously. The probability that the value of the discrete random variable x is 2 is also 3 over 8, which means that 2 tails occurs in 3 events out of 8 possible events. And the probability that the value of the discrete random variable x for the number of tails when 3 balanced coins are tossed simultaneously is 1 over 8. Which means that you get 3 tails in only one event out of 8 possible events when you toss 3 balanced coins simultaneously. And we have also shown that the expected value of the discrete random variable x, denoted by mu for population mean, is 3 over 2 or 1.5. And we calculated the variance of the discrete random variable x, which is equal to 3/4 or 0.75. And the positive root of this variance or variance is the standard deviation, denoted by sigma, of the discrete random variable x, and it's equal to the root of 3 divided by 2, or in decimal number up to 2 decimal places is 0.87. And we continue with this problem by answering this question, the application of Tchebysheff'S theorem. What is the probability that x will fall outside of the interval? This is the open interval with left endpoint mu minus 3/2 sigma. And the right endpoint of this open interval is mu plus 3/2 sigma. And we recall from Tchebysheff'S theorem that at least 1 minus 1 over k squared, where k is greater than equal to 1, lie in the open interval mu minus k sigma and mu plus k sigma. That is at least 1 minus 1 over k squared of the n observations in a set of observations in a set of n observations are within k standard deviations from the mean. Either k standard deviation to the right of the mean or k standard deviations to the left of the mean. Hence, comparing this open interval with this open interval from Tchebysheff'S theorem, we can say that k, the value of k, is 3 over 2. We do not include the negative sign. K is 3 over 2 or 1.5. And using this value of k, we find this exactly what this open interval is. Mu, we substitute mu equals 1.5 minus 3 over 2 or 1.5 multiplied by sigma, the standard deviation, is 0.87. The right endpoint is mu. The expected value of x is 1.5 plus 3 over 2. 3 over 2 is 1.5 multiplied by sigma. Standard deviation is 0.87. And using your calculator, you calculate 1.5 minus 1.5 multiplied by 0.87. And to 3 decimal places, you should get 0.195. Also, using your calculator, you calculate 1.5 plus 1.5 multiplied by 0.87. And to 3 decimal places, you should get 2.805. But we always use 2 decimal places, so we round this off. 0.195 to 2 decimal places is 0.20. And we round off 2.805 to 2 decimal places and we get 2.81. Now, we illustrate this open interval in our probability histogram. Point 20 is greater than 0. This is 0. This is not the origin 0. This is the one of the values of the discrete random variable x. The origin is actually this one, also denoted by 0, and 0 is also one of the values of the discrete random variable x. And 0.2 is greater than 0. And 2.81 is more than 2, just before 3. You have 2.81. And according to Tchebysheff'S theorem, 1 minus 1 over k squared lie in this interval between 0.20 and 2.81. So we calculate exactly what percentage of the n observations if you will repeat this experiment several times or n times, say 100 times, what percentage of these 100 observations or values of x will lie between 0.20 and 2.81. And according to Tchebysheff'S theorem, that percentage is at least 1 minus 1 over k squared. In our example, k is 3 over 2 or 1.5. So we calculate 1 minus 1 over k squared. We have 1 minus 1. Our k is 3 halves or 1.5. 1.5 is squared. And using your calculator, you calculate 1 minus 1 over 1.5 is squared. And this is the result that you should get. 0.5, the digit 5 is repeated without n. And this is what you call a non-terminating, non-repeating decimal number, which is an irrational real number. And to convert this to percentage, we multiply this non-terminating, non-repeat, this decimal number, 0.5, that 5 digit is repeated, is a rational real number. It is a non-terminating but repeating decimal number where the digit 5 is repeated but without n. So this is a rational real number, not irrational. An irrational real number is a non-terminating, non-repeating decimal number. But this decimal number is this decimal number is non-terminating but repeating, where the digit 5 is repeated. So this decimal number is a rational real number, but we give our answer in percentage. So we multiply this non-terminating, repeating decimal number by 100%, and we round it off. We round up the answer to 2 decimal places, and you should get 55.56%. So by Tchebysheff'S theorem, we can expect that 55.56% of the n observations will lie between 0.20 and 2.81. That is, for instance, if you repeat this experiment 100 times, you can expect that 55.55% of 100, the values of x 100 times 55.56% will lie between 0.2 and 2.81. And the possible values of x in this open interval between 0.2 and 2.81 is 1 and 2. So you can expect values of x that are 1 or 2, and these values will occur 55.56% out of the n observations, or if you repeat this experiment 100 times, 55.56% times 100. And the question is, what is the probability that the value of x will fall outside of this open interval? if you repeat this experiment several times, what is the probability that x is outside either less than 0.2 or greater than 2.81? And there are only two possibilities that x will be out of this open interval. That is when x is 0, 0 is less than 0.2, or when x is 3. Thus, the probability that x is not an element of the open interval 0.2 and 2.81 is equal to the probability that x is equal to 0 or x is equal to 3. Since these are the only values of x that are outside of this open interval 0.20 and 2.81. Thus, the probability that x will fall outside of this open interval by addition principle for probability is equal to the probability that x is equal to 0 plus the probability that x is equal to 3. And from our probability distribution or from this probability histogram, the probability that x is equal to 0 is 1 over 8. Plus the probability that x equals 3 from our probability distribution or from this probability histogram, the probability that x equals 3 is equal to also 1/8. And 1 over 8 plus 1 over 8, common denominator is 8. We add the numerator, 1 plus 1 is 2. And 2 over 8 is, in lowest terms, is 1 over 4. We divide 2 by 2, we get 1. We divide 8 by 2, and we get 4. Thus, the probability that the value of the discrete random variable x for the number of tails when you toss 3 balanced coins at the same time will fall outside of this open interval 0.20 and 2.81 is 1/4, or that's 0.25 or 25%. And that completes our lesson for today on the variance or variance of discrete random variable and the standard deviation of discrete random variable and the Tchebysheff'S theorem. And we will continue with in the next lesson with empirical rule that applies only for distribution of observations that whose shape is bell shape. If you have question about the lesson today, you may ask your question in the comments below. But do not forget to subscribe to my YouTube channel, Art Kalism, the channel of learning and leisure. You may also ask your friends, your classmates, your neighbors and relatives to subscribe to my YouTube channel, Art Kalism, so they may learn as well. Thank you for joining me in my class today in Advanced Statistics.